serious stuff, right? Alright, so we're continuing our saga of breaking down objects into tiny parts, measuring those parts, and then adding those measurements up. So we're going to be using the same technique.
Candy. No? Fine, I'll take the Twix. Skittles? Sure. Thanks. I saw you eyeballing them. I fucking my candy.
Okay, so there's a lot of things that you can measure this way. The ones I'm thinking of off the top of my head are arc length, surface area, and work. So we'll be doing all of these things by breaking down the quantity that we're trying to calculate into tiny parts, and then adding those parts. So let's take a look at arc length. Okay, so we know how to find the area under a curve. So far, I don't think we've done anything to calculate the length of the curve. You know, so if I have y equals sine of x, how long is that curve? How much ink went on the board to draw that? Right? So let's use our idea of breaking things down into tiny parts. Now, let's assume that this is my curve. So I'm going to zoom in on one little region of it. Let's say this region. Here's our zoom lens. So between this and this, what am I going to assume is the case right there? I can basically assume this thing is made out of tiny little pieces of straight lines, right? So I can assume that this thing is essentially straight over very short periods. So that is, instead of looking at that curve, I can look at this curve where I just draw straight lines in between these little pieces. So if we can figure out the length of one of these little pieces and then add all of those up, we should be able to calculate the arc length of this curve. So let's see if we can figure out the length of this piece. Now, if I'm integrating with respect to x, odds are very high that this is going to be dx, right? All right, so I guess you could probably call this dy. And so what does this guy got to be? It's going to have to be like square root of dx squared plus dy squared, right? Just because it's a little tiny hypotenuse of a triangle is what we're calculating, the length of. So the length of one tiny, let's call it a polygonal segment so let me call it delta S. It's going to be square root of delta x squared plus delta y squared. Now, if I'm going to get this by integrating with respect to x, I need to get this delta x out here, right? So all I'm going to do, I'm going to divide by delta x squared inside. And then multiply by it. I didn't actually change anything if I do that, right? I just multiplied and divided by the same number. Okay. So what I've got is delta x over delta x squared plus delta y over delta x squared. And if I take this out of the root, I've got delta x. Now, what do you think this is going to turn into when I actually go to calculate the integral?
You get a second delta x from one,
What now?
just one side of delta y.
Oh, like this one? Okay, so all I did was I divided both of these terms by delta x squared and then multiplied by the same thing. So really I just multiplied by 1. I haven't done any harm that way. Alright, so delta x over delta x, well that's just going to be 1. What do you think delta y over delta x is going to be as delta x goes to 0? Right, because this is a slope of what? Of this little tiny line segment.
Have you changed it?
So it should just be the derivative, right? As your 2 points get closer and closer together, the slope of this line becomes the slope of the tangent line, right? And so this is going to look like dy dx squared. And of course delta x is just going to turn into dx. So this is what we're going to be integrating to calculate arc length. I know that's kind of a handy wavy argument, but that's basically what we're measuring. Is this should be the length of one tiny piece of arc length. So if we can do that and then integrate it, we should get the whole arc length of the curve. I would say let's try this on a couple of curves that we're familiar with to see if we can make this happen and get known results out of it, check and see if it's working. What's something that we already know how to get the length of? Yeah, we could do circumference of a circle or maybe just like length of a line. So let's take a look and see if this is doing the right thing.
So yummy.
So example. Okay, so let's do this. I do y equals 3x plus 1. That's a line with slope 3. Right? So if I'm looking at it from x equals 2 to x equals 5, my arc length should be the integral from 2 to 5, square root of 1 plus dy dx squared dx. Alright, so what is the derivative of y with respect to x in this case? Just 3, right? So it's going to be 1 plus 9, so I've got square root of 10 integrated from 2 to 5, right? Now if I'm integrating a constant, I've just got square root of 10 times the difference in the endpoints, 5 minus 2, so it should be 3 root 10. Let's see if that matches up with how we know how to find the arc length of a line. Right, so what is this point? This is 2 comma, what is that, 7? And this will be 5 comma 16. Okay. So the actual length should be the square root of what, 16 minus 7 squared plus 5 minus 2 squared. Alright, 16 minus 7 is 9, so I've got 81 plus 9, is that right? Okay, so I've got square root of 90. Now I can take out a 9 out of that. This is square root of 9 times square root of 10, which of course is 3 root of 10. So it does seem to be matching up, but again, the same argument for Pythagorean theorem works for straight lines of any length. Yeah?
How'd you get 9? Is dy divided by dx essentially the same as x2 minus x?
No. It's dy dx as in the derivative of this guy with respect to x.
Okay.
Yeah, because as your dx goes down to 0, as we get to the limiting concept, that slope of that tangent line is going to become or the slope of the secant line is going to become the slope of the tangent line. It's a derivative. So, all right. Yeah, again, the other argument of that is, what does dy dx mean? Essentially, I'm approximating the curve by its tangent line right here, right? And so if I want to know how far did it go up, well, I know dy is approximately dx times f prime of x, right? So I'm using that approximation. I'm approximating the function by its tangent line. All right, let's try this for a harder one. Let's see. Do we dare attempt the circumference of the circle?
I guess we're gonna.
Yeah, we're gonna try it.
Okay.
Now this might go off the rails. I don't know. So forgive me if the computation just turns horrendous, but let's give it a shot.
I got candy.
I didn't do this beforehand, so I don't know. Let's see. Now, if I've got a circle, radius r, that is x squared plus y squared equal to r squared, right? So, for example, if I wanted the top half of that circle, I could do y equals square root of r squared minus x squared. That's this curve here. So if I could find the arc length of that, then I should be able to just multiply by 2 and get the circumference of the circle, right? All right, so what do I need to do? If I'm integrating 1 plus the square of dy dx, well, I need to calculate the derivative of this function. So from here, dy dx is what? I got 1/2 times r squared minus x squared to the negative 1/2 times what else? Negative 2x with chain rule. Is that right? Okay. So what I've got is negative x over square root of r squared minus x squared. This might work out okay. We'll see. So what I want is ds, a small amount of arc length. Anybody know why they use s for arc length? They always do. I don't know why. What's it?
In physics, we use like S is equal to R.
Yeah, okay.
For the planets, to measure the planet distance from, so it's like S is like the arc length, R will be the radius of the planet.
Yeah, okay, yeah, so it's like a distance around the outside of a planet. What does that have to do with S? I don't know. Yeah, all right, so.
Space. It's some space.
S for something, yeah, so, all right, so. I mean, you know what my problem is? My S's look like 5s, my 5s look like S's. It's, you take a differential equations class, you do Laplace transform, everything is in terms of S's, right? So you're supposed to get an answer that's like a function of S, but I would get answers where everything canceled out and it was like 42 as the answer. And it was because somewhere up here all the S's became 5s and then they just got canceled out of the computation. So it's an easy thing to let happen. So it's supposed to be 1 plus y prime squared, right? Okay, so what I've got is the square root of 1 plus the square of this guy, which will be x squared over r squared minus x squared. Okay. What, common denominator, I guess? So this would be square root of r squared minus x squared plus x squared over r squared minus x squared.
Why didn't the negative
Squared.
Yeah, because it's squared, yeah. So these two x squareds ought to cancel out. So what I've got is square root of r squared over r squared minus x squared. Okay. Okay, so this is r over square root of r squared minus x squared. Is that reasonable? Yeah, because r is going to be positive. We can just pull it out. All right. So this is what we're having to integrate. So who knows how to do this integral?
Check.
That's a trig sub, right? So arc length is going to be the integral from negative r to r of, it looks like, r divided by square root of r squared minus x squared. So what's your trig sub anyway? It's going to be sine, right? Because the x is negative, so it's going to be r sine of theta.
Cosine theta.
And yeah, so yeah, dx is going to be r cosine theta because r is constant. And this guy here, square root of r squared minus x squared, that's probably also going to be r cosine theta, right? Remember how that comes off of the triangle? Because what I've got is x over r is sine of theta. So that's my triangle. Yeah, so if I divide this by r, I get cosine of theta, so it's r cosine of theta. All right. So this guy is going to turn into the integral of what? R times dx is r squared cosine theta, d theta. And the guy on the bottom is going to be r cosine of theta. Okay. So r's cancel out. I got one left over on top. I'm just integrating d theta. What do my limits of integration become?
Cosine negative r, cosine r.
Let's see. If I know that x over r is sine of theta, right? And so when x equals negative r, that means sine of theta is equal to negative 1. So what's theta?
Pi over 2.
Yeah, negative pi over
Negative
2,
pi over
right? So I'm going to go over the right-hand side of the circle. I'm going to go from negative pi over 2 to pi over 2. So theta is negative pi over 2 in that case. And also, when x is positive r, that means sine of theta is 1, so theta is pi over 2. So really all I'm integrating is d theta from negative pi over 2 to pi over 2. Alright, so I should just get r times the difference in endpoints, which is r times pi, and that was half of our circle, right? So if we get 2 pi r, that's what we're supposed to get for the whole circle. So this is the length of a semicircle. Okay, so it's working out so far with things that we've seen. Suppose we try one that it doesn't do this. Let's try and find the length of something fairly benign like a parabola. That seems easy enough. So on the length of the curve y equals, say, x squared for x between negative 1 and 3. So something looks like this. We're just trying to find the length of that curve. Okay, so dy dx is 2x. And so the s, small unit of arc length, is going to be square root 1 plus 2x squared dx, aka 1 plus 4x squared under a radical dx. Okay, so what kind of thing is this? Another stinking trig sub, right? So this is a place where trig subs do kind of crop up fairly often. So arc length is going to be the integral from negative 1 to 3, square root of 1 plus 4x squared dx. What's my substitution here? Yeah, it's going to be a tangent, so I need, what, probably a 2x and a 1, and then the square root of 1 plus 4x squared. Would that do it? Okay, so 2x over 1 is going to be tangent of theta. And so x is going to be 1/2 tangent of theta. Now that also means that if I do square root of 1 plus 4x squared, if I divide it by 1, that is what? Hypotenuse over adjacent. So that's going to be secant theta. And what else am I missing? Dx. So dx is the derivative of 1/2 tangent theta, which is 1/2 secant squared of theta. Okay. So arc length is going to be the integral from somewhere to somewhere. I don't think my limits are going to be particularly nice this time. So I don't know where I'm going from, but let's put some placeholders in here. And I'm going to be integrating, it looks like 1/2 secant cubed theta d theta. So that's the next question, is how do we do this? Yeah, you had to use an integration by parts and a trig sub, right? You remember this nightmare? Alright, so let me just do this as an aside. The integral of secant cubed of theta, well, you could do it as the integral of secant squared theta times secant theta d theta. Now, if I do an integration by parts on that, if I do u equals, well, which one do I want for u and which one for dv? What's better to integrate, secant or secant squared?
You can
Secant squared is a whole lot better to integrate,
'Cause you
right?
know what's going
So
on.
let's do dv equals secant squared theta, d theta, and then u is just secant of theta.
can't be like secant square theta is tan square theta.
What's it?
Tan square theta plus 1.
Yeah, I'm gonna do that too.
Oh.
I'm just doing the same thing, but in the reverse order.
Okay.
Remember, you need both of them in this. So du is secant theta tangent theta, d theta, and then v is tangent theta. Let's see where this goes. So this is u times v, so it's secant theta tangent theta minus the integral of v du, which is the integral of secant theta times tangent squared theta. And here's where I'm going to use that same trig identity. So I'm going to get this as secant theta tangent theta minus the integral of secant theta. What's equal to tangent squared? Is it secant squared minus 1, or is it secant squared plus 1?
Is it 1 plus secant?
I can't remember. I gotta do this every time. Alright, this says tangent squared plus 1 is equal to secant squared, right? Okay, so tangent squared is equal to secant squared minus 1. I have to reconstruct that every time. So, this is secant theta tangent theta minus the integral of secant cubed d theta plus the integral of secant theta d theta. And all of this is equal to the integral of secant cubed, right? So what was your punchline?
Add secant cubed.
Add secant cubed, add the integral of secant cubed and divide by 2, right?
Yeah.
So what you're going to get is the integral of secant cubed of theta d theta was a half of what was left. So it's a half of secant theta tangent theta and a half of, what's the integral of secant? Natural log of secant theta plus tangent theta.
Okay.
Okay, so that's what we're dealing with. Okay, so what I need to do is this needs to get multiplied by a half, because I had a half out here. So I'm going to end up with 1/4 secant theta tangent theta plus 1/4 log of secant theta plus tangent theta. And that was evaluated at our placeholders. So I have to go back to my original variable just because otherwise I get secant of the inverse tangent of some garbage, right? So you had to go back to the triangle. So let's remember what that was. I think we had a 2x here and a 1 here, is that right? Okay, so that means tangent of theta is 2x, and it means that secant of theta is square root of 1 plus 4x squared. Okay, so we can finally translate this in. I got 1/4 times 2x times the square root of 1 plus 4x squared plus 1/4 natural log of 2x plus square root of 1 plus 4x squared. And that is what I'm going to evaluate at -1 and 2. Because that's the arc length of the thing that I'm finding. Alright, so let's punch it in.
Okay.
Alright, so if I plug in at 2, what do I have? This is 2/4 is a half, times 2 is 1, times the square root of 1 plus 16, okay, plus 1/4 natural log of 4 plus the square root of 1 plus 16. And then when I plug in -1, I get plus 1/2 square root of 1 plus 4. And what? Hold on, that's minus negative, so it's plus minus 1/4 natural log of -2
Swipe.
plus the square root of 1 plus square root of 1 plus 4. Okay. So I've got square root of 17 plus 1/4 natural log of 4 plus root 17 plus root 5/2 minus 1/4 natural log of absolute value of -2 plus root 5. Okay, so that's the length of that curve. So, don't know what that is, but it's a number, and it is actually the length of that parabola from -1 to 2. So you never know what's going to blow up. If you have a very simple looking curve, the computation can just be astronomical. But sometimes you can get an uglier curve that works out in a better way. So let me show you what other things you can run into besides just trig subs in here. Can you see where trig subs are naturally going to turn up? Because in my formula, I've got the square root of 1 plus something squared. So it looks like a quadratic under a square root. All right, so the other thing that can happen besides this, let me just give you an example. I think this is the one. 1/2 e to the x plus 1/2 e to the negative x. For x between, let's say -4 and 4. Alright, so you know what this function looks like? This is a hyperbolic cosine. I think it looks kind of like a suspension bridge kind of a shape. Alright, so it's symmetric left to right. It's kind of parabola looking, but it's not exactly a parabola. Alright, so same analysis. We gotta find the derivative of this creature. This is 1/2 e to the x minus 1/2 e to the negative x. Right, just because it just changes the sign on this term when I differentiate, otherwise it looks the same. So if I want the square root of 1 plus derivative of y squared, it's going to be the square root of 1 plus 1/2 e to the x minus 1/2 e to the negative x squared. This is the guy we've got to integrate, so any amount that we can simplify is going to be fairly helpful. What's it? Yeah, something's going to cancel if you pull it out. So let's go ahead and multiply this out. This is the square root of 1 plus. So I'm squaring a binomial. I got to have first term squared, the product of the two, which will be minus 1/2 times 1/2 times e to the x times e to the negative x. So it's twice the product, right? And then last term squared, which will be 1/4 e to the negative 2x. What's that term in the middle? These two cancel. These two cancel. Can you see where that's just minus 1/2? So I've got the square root of 1 plus 1/4 e to the 2x minus 1/2 plus 1/4 e to the negative 2x. And you can see exactly what's going to happen here. You see that your positive 1 just flips a sign on this middle term. So this is actually 1/4 e to the 2x plus 1/2 plus 1/4 e to the negative 2x. And what's the punchline here? Compare that to what we started with up here. You see where it's a perfect square inside the square root? So I've got the square root of, if I take 1/2 e to the x plus 1/2 e to the negative x and square it, that's exactly what I've got. So it's a real common trick in these kinds of problems. Either you're going to get a trig sub, or you're going to get, sometimes a u substitution comes out if you do it just right. But this is also a really common trick. So this whole thing, square root and square cancel out, and you just get 1/2 e to the x plus 1/2 e to the negative x, which ironically is the function you started with. So if I want the arc length of this guy, all I have to do is integrate the function we started with, the -4 to 4. And it turns out that's super easy. So this is 1/2 e to the x minus 1/2 e to the negative x, evaluated at -4 and 4. I can go ahead and factor out that 1/2. Alright, so I've got e to the 4th minus e to the -4th. And then on the bottom, I've got e to the -4th minus e to the 4th. Okay, so do the terms cancel out or double up? They better double up, right? Just because metalogic, the arc length of this thing is not 0. So